On fluid flow over a flat plate, both laminar and turbulent regimes can occur. If we have this flat plate, let's say there is a uniform flow with the U infinity passing over this region, initially we can have a laminar flow at the beginning, at the entry, where in this laminar flow, the velocities vectors are highly ordered, they are essentially 2D. And then we can face a transition zone when the velocities are no longer highly ordered, and after that we can reach to a turbulent conditions where the mixing is happened by vortices. So this is the first region where we have laminar flow. Let's assume this is X, and we can have a transition zone, and from here we can have turbulent flow, turbulent regime. In turbulent regime, what we can see here is the flow is highly irregular and characterized by the random 3D motions, and through this mixing happens through these vortices. In fact, in the turbulent regime, we can define 3 layers. The first layer is very close at the surface or very close to the surface wall, and that's what we call a viscous sublayer. This is the viscous sublayer, and this is dominated mainly by the diffusion, and velocity profile is linear. So viscous sublayer diffusion profile is linear, and above this viscous layer we have a second one, we call it buffer layer. And that's essentially the transitions from this viscous sublayer to the turbulent one, and the mixing happens by both diffusion and turbulent mixing present here. And above that, this is where we have the turbulent zone. Where it's dominated by turbulent mixing. Now, if we look at the velocity profile, let's say for a laminar case and a region that we have here. So if we draw the velocity profile for the laminar, we have seen it. Start from 0, and then we have a change. Let's say this is 0.99 U infinity. Now, if we look at the same velocity profile, sorry, the velocity profile for the turbulent region, what we are going to see is essentially flat velocity profile is exaggerated. So velocity profile in turbulent flow is nearly flat. So here u of y is nearly flat, and that's because of the turbulent mixing that we have in the buffer and turbulent region. And close to the wall, we have this sharp gradient. So let's say this is the gradient, du dy at y equal to 0, and you will see that's the du dy at y equal to 0. Now, if we compare, since we have this really sharp increase of the velocity till it's reached to the u infinity, what we can say here is du dy by 0 is smaller than du dy at y0. This is for the turbulent flow, and this is for the laminar flow. What does that mean? Is the wall shear stress for the turbulent is greater than this wall shear stress for the laminar. Now, the transition from the laminar to the transition and then to the turbulent flow, we can find that and characterize it by Reynolds number. Let's say this is xc, where we see the transitions that's happening, and we define that by u infinity x divided by nu. We call this one Rex, or Reynolds number, and nu is the kinematic viscosity, which is the ratio of dynamic viscosity divided by fluid density. Now, the Reynolds number justifies in or shows the inertia force divided by viscous force. Now, for a flow over a flat plate, typically the Reynolds number, let's say at xc, should be greater than, define it, u infinity xc divided by nu should be greater than 5 times 10 to the power of 5. Of course, the value varies, depends on the geometry, the condition of the flow that is entering. Not always it is uniform. It can bring some vortices or some irregularities in terms of the flow inside that. But the value that we are going to stick to for the laminar versus turbulent for flow over flat is 5 times 10 to the power 5. That's that's one thing. And the relevance to the heat transfer here is that similar to what it can cause to the velocity profile. Let's say from this laminar flow to turbulent flow, that we see there is a sharp velocity gradient that results in the increased shear stress, wall shear stress in the turbulent conditions. Now, if I plot the heat transfer coefficient, so let's say I have this flat plate, and this is the laminar, this is the transition, and this is the turbulent. So this is laminar, the transition, and from here we have the turbulent. The turbulent flow regimes, or the turbulent regime, what it can does from the transition to turbulent, it can cause a sharp temperature gradient, and because of that, let's say if I plot here, Hx, the local convective heat transfer coefficient, and let's assume it has this profile in the laminar zone. Now, because of this sharp temperature gradient, what we are going to see, we're going to see an increase in the value of H that happens here. So this is H of X as a convective heat transfer coefficient, and this is delta F. This is the hydrodynamic boundary layer in the system.